first thing I wanted to do is problem 3 dash, 3-5.3, because I didn't do that last time, and I want to tell you this now, just straight up front. This last part of the course conceptually is more difficult. It will throw you. You've got to keep up with this, because this is the stuff come final exam. You can absolutely be, I don't know where to begin if you don't keep up with it. I'm telling you this because I've taught this course 3 summers, I think this might be my 4th summer. When I teach random and stuff, or when I deal with random and statistical stuff with radar, it's much different. It's very applied. The actual problems, I can more or less carve out what you need to know from. But these are getting into some crazy things, some very, I'd say, challenging things mentally. So, did anybody try this problem? 3-5.3. Now it's in that section that I'm sure is up on the homework now, but I'm sorry I put it up late. I want to go through this. We'll go through as many as we can. I want to get through section 3-7 so we can move into chapter 4 today. But I'm hitting the problems I think are most conceptually difficult. So with that, and if you have any questions, don't be afraid to stop me, because there are no dumb questions here, believe me. All right, so for this one, they're going to give you some x of t equal to just cosine of omega t plus theta, and some y of t equal to cosine of omega t plus psi. I'm going to just call it that. And then they give you a value z of t. I'm calling it z, it doesn't matter what you call it. It's going to be some a cosine of omega t plus, and he uses the symbol phi, and he says that's equal to cosine of omega t plus theta plus cosine of omega t plus and psi. Okay, now he has some questions for you. First, he asks basically, we're going to have to first solve for A, then he wants the probability of A, and I think it's greater than 1. Yes. We're going to get to that. This is the essentials of the problem. Now, it's in your book, and I hope you all, I think you can do, I don't know, like these people, the people that keep notes on your tablets and stuff, you can probably go into that PDF and just highlight, do the snippet thing, snip out the problem and restate it in your notes, and then you can go from there. But just a suggestion. Now, if you look at this problem, and it's, by the way it is, here's the first thing you do. You see how omega t is common to all of those arguments, those cosine arguments? Everybody see it? Just get rid of it. You don't need to worry about that. That is a distraction. I get rid of this, or I make t 0. It's got to be true all the time, so it's true for t equals 0. And this will help you, I think, see how to get to the real core of the problem, the essence of the problem. With me? Now we got to solve for A, and I want to tell you this. Hey, CJ, your quiz is up here if you want to. When you're solving for this A, the whole deal is, I'm just going to even get rid of Z here. When you're solving for A, what you really need to do, you could go ahead and mess with, angular identities. Follow me on this one? It looks like we're probably going to do something funny with cosines, if you know what I mean. But here's the real way to do it. Think in terms of a complex number. Remember, cosine of phi is just equal to, or a cosine of phi is the projection of a e to the j phi on the x-axis, think of it that way. And a times the sine of phi would be the projection on the vertical or y-axis. Do y'all follow me on this? You know what I'm talking about? All right. I'm going to try to draw this up and make it real clear, because I did this thing cold some time ago, and the way I did it, he does it similar but different. So here's what I'm going to do. When I look at this, all these things, I can say what this really represents is equal to some a e to the j phi is equal to really e to the j theta plus e to the j psi. You all with me on this, class? Now, if you take the projection of that, if you just take the, expand this in terms of sine and cosines, you all follow me? If you do this, you get a cosine of phi is equal to cosine of theta plus sine of psi, or plus cosine of psi, with me? And if you just take the projection of the vertical axis, you'll get this. But the reason I'm showing you this trick, this is x, and this is the vertical axis. I shouldn't call it y. Maybe I'll even, no, I'm going to use small x, small y to indicate this. So when I have the first one right here, e to the j phi, it's this. There's an angle phi, and this vector length is 1, and this would be e to the j phi. And then on top of that, you're going to have some e to the j psi. Can you all see this? I'm just plotting these two complex numbers. They both have a length of 1. And that's equal to a, just look at this. This is the way to think about this. Let's see if this actually works. And if you look at this, this is a e to the j phi. Can everybody see that? Does everybody know when I'm plotting e to the j theta, that's magnitude of 1, and it's at an angle with respect to the horizontal or real axis. You could call this, you may want to just call this real, and this imaginary. But I have to get the perpendicular axis to show you what I'm talking about. Does everybody understand that, class? You all in the back? CJ? Well, when you do this, follow me. If I take the projection here of these things, this distance here would be a cosine of, it should be theta, I'm sorry. This should be theta right there. And this would be, it would be 1, just cosine of theta. And this would be cosine of psi. And then when I take a down here, this distance would be a cosine of phi. And likewise, for the vertical axis, the vertical component of this one would be just sine of theta, and the vertical component of this one added to that would be sine of that should be psi. Oh, no, that's phi. It would be sine of psi, so this is, maybe I'm going to put it down. This would be equal to the sine of theta, and this distance would be equal to the sine of psi, which would be equal to this distance, which would be a times the sine of phi. Now, can everybody follow me what I'm doing? And you know one thing about right triangles. A squared plus b squared equals the actual hypotenuse squared, correct? What's the hypotenuse on this triangle right here? You can see it. When I look, that is A, isn't it? And that's the angle phi. Can you all see this? This one right here? How many can see what I'm up to? You with me? Anna, can you see it? And everybody? Anybody not see it? Now here's what I'm going to do. I'm going to take this side here and square it, plus this side and square it, and set it equal to a squared. Can you all follow me? The reasoning. He does something like this in the answer, in the solutions. He kind of shows you that, but he doesn't go through the actual operation in detail. So I'm going to come over here and do it. This marker's a little better in terms of how clear it is on the board, so I'm going to use this one. So when I look at the horizontal one, I have just cosine of theta plus cosine of phi. That would be the horizontal component. Can you all see that? Now I'm gonna square it. Don't worry about that A business. So I'm gonna square it. And when I square it, I'm gonna get a cosine squared of theta plus a cosine squared of, not phi, but psi. Greek is not the best. Plus 2 times cosine of theta cosine of psi. Now the reason you get 2 is because you multiply this times this once, then again, and you're gonna get a 2. Can you all follow me? How many understand that? All right, just to be clear about it. Now go down below here, and when I take the vertical component and square, or the imaginary, it's gonna be the sine of theta plus the sine of psi squared, and almost identical to this, except the signs, you're gonna have sine squared of theta plus sine squared of psi plus 2 times sine of theta sine of psi. Can you all follow me on this, class? So now this is like the horizontal part of the real component squared. This is the horizontal component squared, right? And we know when we take this component squared plus this component squared, we get A. You all follow me? Just the hypotenuse. So, or A squared. So now I can say that A squared is equal to, and look, I'm going to have to add these together, and I think you can see this. When I add these together, what is cosine squared theta plus sine squared theta? 1. It's beautiful coming out this way. So it's going to be 1 plus, and when I add cosine squared theta plus psi, or cosine squared psi plus sine squared psi, I get 1 plus 1 plus, and then when I do this, right, I have plus 2 times the quantity cosine of psi times cosine theta, cosine of theta, cosine of psi, plus sine of theta, sine of psi, as a factor of 2 there. And let me get this for you. Well, the 1 and 1s are great because that's just 2, right? This is going to be 2. I'm trying to make the best of the time. So this is 2 plus this, right? This is one I had to look up. If you have a cosine of A minus B, that's equal to cosine A, cosine B, and then it would be plus sine A, sine B. Those identities I don't remember right off the top of my head, but I'll tell you a trick that always works. Now I know Euler's identity. Remember this one thing. If you're ever looking for a half angle identity or something to do with that to make it one thing, here's what you can do. I can say that the cosine A minus B is really e to the j A minus B plus e to the minus j A minus B over 2. First, you agree that's the cosine of A minus B. The only thing I did is use Euler's identity for that, right? Now, when you multiply these out, you get e to the j A times e to the minus jb, e to the minus ja plus e to the plus jb over 2. You can get rid of that too. And then you can factor a few things out, but you get a cosine. You get a cosine out of that mess. Now, it takes a little time, but that's how anytime, like when I was sitting where you are or in graduate school, if I needed an identity, and most of the time it's closed book, closed notes for everything, almost always. So you had to work it out on your own, but that's where I'd go. Just remember this. I'm not going to work the whole thing out, but you'll be easily able to see that you're gonna get a cosine A, cosine B when you factor this thing, because there's an e to the JA plus e to the minus JA over 2. That's cosine right there. And it takes a little while, but you can get it. So that's the truth. Now here's the reason I did this. Now I can say that a squared here is equal to 2 plus 2, and this is going to be cosine of the arguments, which is going to be theta minus psi. You with me? You can see how we're basically going to use a lot of trig stuff. Yeah.
What happened to the cosine phi? The one that was attached to the a squared?
What?
Where, because you were given a squared is omega t cosine phi, right? I was just wondering what happened to it right there.
Okay, right here?
Well, so that
There's
we
no
just
omega
set it
t.
equal to a squared.
What's it? This whole thing's a squared, right? This, if you take a look at this, add this and this, that, I erased it. It's the horizontal component squared plus the vertical component squared, right? That's the hypotenuse. The hypotenuse is A.
Okay.
All right, that's the point. Y'all with me? I'll draw that triangle right here, but at the end of the day, this is phi and this is A, and this side is just cosines and this side is just sines. So when you square vertical and horizontal and add them, you get A squared. We have to figure out what A squared is, but here's the next step. How many remember? Now, I'm pretty sure you do, but you might be a little unsure. If you have cosine squared of x, that's actually 1/2 plus 1/2 cosine of 2x. Do you remember this stuff? Do you remember how you check that always? I mean, we could do it with the exponentials. We could, write down what it is for. You could use the Euler identity for cosine squared, but here's the way I always do it. I let x equal 0. Cosine is 0, it's 1, 1 squared is 1. Over here, I have 1/2 plus cosine is 0, 1/2 it's 1. Checks that box. Then go to 90 degrees. All right? So, if you look at this, the cosine of 90 is 0, right? Squaring 0 is 0. The cosine, this would be 180. Cosine of 180, right, is going to be minus, right? Then you get 1/2 minus 1/2, minus 1 there. Y'all with me, class? So you can check, I always checked it like in my head if I have to be sure. Back to this thing, you can see what this really is now. Is going to be a squared, and what I'm going to do is factor out a 4, and then I factor out a 4, I get 1/2 plus 1/2, and this is going to be cosine here. And what I have to do is divide that by 2, so it's going to be theta minus phi over 2. Now I'll tell you what I've done here. I'm using this identity. And I can see I have this, and my argument 2x is actually theta minus phi. I'm going to stop for a second. What I'm really saying, I'm looking at this thing, I pulled out a 4, so I have 1/2 plus 1/2 cosine, whatever this is, wait a second. Yeah, I did that right. Hold it. No, sorry, I did that wrong. That should just be that. I'm sorry about that. What I'm saying is this should be 1/2 cosine of this. I'm sorry about that. Y'all with me, class? It's just this argument brought down here. I factored out 4. So there's 1/2 in front of both. Y'all with me? Now the next part, I'm getting ahead of myself. Now I'm going to use that identity. This is on the right side over there. So 2x is equal to this, right? And I come down here and that makes a squared here equal to 4, and this would be cosine squared of that over 2. If you look at that identity, it fits here. Y'all follow me, class? just look at this. This 2x right here, you equate to this argument. Can you all follow me? That means half that argument goes here if it's a cosine squared replacement. Follow me? Okay, now if you get that, I need A, and here's the thing. That means A itself is simply, if I take the square root of that, I get 2 times cosine of theta minus a sine over 2. So now, lo and behold, yeah.
Okay, sorry, I'm getting a little lost.
I understand.
So from the top there, is that, look from point A up top,
When you say top there,
like over here? The
You talking about this?
No, on your left, up top.
to this.
So that to point B, the second part.
Here, look, right there,
Mhm,
okay, that's this. See?
mhm.
All right, now, what does that equal to?
Okay.
A minus B.
So that's an identity, okay. And then from that
From here,
to the next part.
yeah. I factored out a 4. If I factor out a 4 to get a 2 there, I have to have a 1/2.
Where did you factor out a 4 from?
Right here. If I factor out a 4, I get a 4, right? Follow me? So I get 4. 4 times 1/2 has to be 2.
Oh, you're just,
4 times 1/2 has to be 2.
oh, okay.
I've got to fit the form. That's the reason I'm messing with this week. By the way, this is an irritating problem if you're tired. I did this.
Oh, and then you divided by 2 to get the,
There's 2 or 3 identities here. First, that's the one over there with that triangle. That's the key. Then you can go nuts on trig identities just looking at something that'll fit the form of the original. But this works. Y'all with me, class?
Yeah, he just takes the square root.
Just take a moment and as best you can convince yourself. Trust me, this part is right. Okay, so that's A. After all is said and done, that's A. Now it gets interesting. It's like all that work to get A, we're just not even a quarter of the way done with the problem. It gets more interesting. And at least some of you should be thinking, are we expecting trig identities like this for any quizzes or tests? If you are, I will give you trig identities. These are kind of crazy trig identities. Euler's, basic Euler's is fine, but I'm not gonna ask you something that's gonna take, 20 minutes to fuss with Euler's to get. So what I'm telling you is I'll be fair about that. Back to that thing right there though. Now they want the probability, I think, that A is greater than 1. Elijah, tell me, or, Jagger, is that right?
Yeah, that's the first one.
Yeah, that's the part.
oh, the second part, find the probability.
No, it's the first part. It's part A, isn't it?
Yeah, so, find the probability is greater.
So now, it's like, okay, now that we've got a form for A, what does A represent? Well, this is what? Better yet, instead of A greater than 1, how about we divide by 2? And we make this 1/2. So 1/2 probability is greater than 1/2 of this. That's a cosine waveform. Y'all with me? Can you all see this? Now what I'm going to do is this, and he does it too. I'm going to say that A is equal to 2 cosine, and he uses B. And B is just equal to theta minus sine over 2. He's doing a replacement there. So if we look at that, and I want to be clear about this better yet. Let me just leave it with this one right here. I'm going to go ahead and just write A. Here is 2 cosine B, and B is equal to theta minus sine over 2. I've got it there already. And now what I'm going to do is graph. Problem is, if I look for this, what I'm really looking for is, if we're looking for the probability of A greater than 1, we could divide A by 2, and it would be a cosine B greater than 1/2. Can everybody see that? So what I'm going to do is just plot cosine of B here, and I'm going to go from minus pi to pi, because that way I can stay, in a relative sense, I can see what's going on easier. It's symmetric. Cosine's an even waveform. I don't do this. it's kind of a problem. If I gave you the identities, I'd give you time to do it, but it's a reasonable problem. Just trying to clear about this. And this is the kind of complexity we're gonna get into in a lot of this stuff. It can drive you a little nuts if you aren't sharp. For this one, it's asking the probability of that waveform greater than 1/2. Well, 1/2 is right here. Can you all see that? And what that is, if you take cosine B as 1/2, just set that equal to 1/2, you're gonna find that is gonna be 60 degrees or pi over 3 right here, or 60 degrees. And this part right here would be minus pi over 3 or minus 60 degrees. Everybody with me on that? Now really the probability that I'm trying to show you how B will relate to this. The probability of A being greater than 1/2 is going to be the probability that B is between here and here, or B is between 0 and 60 degrees. Can everybody follow me on that, class? Y'all? So really what I need is the probability of B right there being, not greater than, B being between, or 2 times the probability of B being greater than 0, less than 60 degrees, or pi over 2. I'll put pi over 2, or I'm sorry, pi over 3 radians. That's what I really need. So after all that, what it really boils down to is we got this information. It becomes the essential of the problem. With me, class? You had to mess around and trick to get A. After you get A, now we figure out what he's talking about in terms of angles. Y'all appreciate this? Now here's what he talks about the angles. He says that the angles have density functions that are flat. I'll do it over here. And what they say is really f of theta is going to have the same exact form as f of psi, and it's going to have a value of 1 over 2 pi from 0, or I should say from 0 greater than that value of either psi or theta less than 2 pi. So both of them look like this. If I put f of psi down, it would look like this. And f of y would look the same exactly. It would be 1 over 2 pi from 0 to 2 pi. Y'all with me on this, class? Now, it gets fun. Well, not fun, but it gets interesting. So, what erase this? So now, I erase B. So B itself was equal to theta minus phi over 2, right? And I'm going to do something. I'm going to say this B here looks like theta over 2 minus psi over 2. All right? Now think of this. Think of this as a unique variable. Doesn't matter what you call it, and this is a unique variable. Let me be real clear about this. Just call this like x prime, and this y prime. There's a little more to this in a second. But if I do that, then these density functions will change. Then I'd have something like this. From 0 to pi, and the height of this would be 1 over pi, and this would be my fx prime. Down here, it would be f prime, and it too would have a height of 1 over pi from 0 to pi. And by the way, the argument in here, whatever the horizontal argument, could be psi, it could be theta, it could be x, doesn't matter. When you plot whatever this variable is in f of x prime of that variable, you'll get this plot. You all understand basically compressed one axis and doubled the other. Can you all follow me on this? Because if you think about this, let's look at theta. If theta is from 0 to 2 pi, if I divide by 2, it's from 0 to pi. And for a density function, it always has to have an area under 1, so the height doubles. Can you see that? Are you with me, Elijah? I'm just making sure. What I'm really trying to do is carve this into something that is doable. Now here's the trick on this one. If you look at this right here, I have b is equal to, and I'll call it x prime minus y prime, right? Remember, if you have a function of x minus y, it's not convolution, it would be correlation. Y'all with me? In other words, to be really clear, if you have a variable z is equal to x minus y, then, and you have density functions here, f of z would actually be equal to an integral of f of x, well, I'll call it lambda. You don't have to write this down, I'm just going to get to a point. And then it would be f of, and here it would be z plus lambda of y, d lambda from minus infinity to infinity. That plus sign inside there is correlation related, and that is not the definition of convolution. Can everybody follow me? How many can? You know the definition of convolution. By the way, this is critical you know this, especially in the upper level classes. You're going to have Dr. Tugman for communications, and I'm not sure what all the upper level classes you're taking, but it becomes imperative that you know the definition of convolution, because they use this, and they use Laplace transforms for almost everything, a lot of it. So, you know, for this one, we would like that to be minus because we're very familiar with convolution, how convolving two functions in one domain is multiplying them in the transform of the estimate. That's really nuts because we hate convolution. I hate convolution. So if you look at this, what I really want is a plus here. And the way I do it is this. Follow me on this. Instead of having this function, what I'm going to do is make it a plus, and then make y double prime equal to minus y prime. Now here's what that entails, and I bet you some of you can see this. What I'm really going to do is take this density function for y prime. I need y double prime is minus that, right? Can you all focus on it? By the way, this kind of problem is going to come at you, so pay attention. I don't know how to get you to pay attention sometimes, because this really is a tedious little problem. So now I flip that, and I can convolve them. So if I look at this, here's the function right here, and that's f of y double prime. Same height, 1 over pi, but it starts at minus pi here. Everybody with me on this? It's still an irritating problem, but now we need to convolve those. Let me show you a trick with this. These are two identically shaped functions. We call them boxcars. And the whole idea is this: if you're convolving two functions, pick one and don't shift it. I'm going to do that one, right? Top. Maybe. Actually, I'll pick this one. I'm going to pick that one. And this is going to be now my f of y double prime. And it will be, I'm going to use tau versus tau. Now, and that one looks just like this. This one is just negative, from minus pi here to 0, height 1 over pi. Now I come down here, and I take this one, but I have to flip it. You with me? Because now I need my f of x prime of, and this is going to be something where I'm going to have z minus lambda. Remember, you first take, this is the one I'm gonna flip. So when I flip it, it's gonna go here, right? And that would be f of x prime of minus lambda, or minus tau. And then I have to add that shift, so it looks like this. This point would be z, and this point down here would be z minus pi. The height of this would be 1 over pi. This is the little boxcar thing. These are really nice to do. I'll go over there. I'm really trying to work through this one time with all the details, because you can obviously see instead of that, like, instead of a cosine of some angle equal a couple of cosines, I could make it a sine. You all with me? I can do stuff where I can make that any kind of trig relationship, and you can follow suit and get this. But ultimately, this is what we need to get, this information. We need the f of z. All right, so if I look at this, now, better put this down. My z, or b actually, is equal to beta over 2 minus psi over 2, which is really my x prime plus my y double prime is b. And now I'm going to convolve these things and get an f of b. That's basically it. B is a variable, just like c is a variable. Come down here, and when I do this, remember, for this whole thing, these are the two functions, and I can call it f of b. So f of b here has to do with, if you look, it's you have to take the actual function here, multiply it by the function here, and then integrate it point by point. You with me, class? So you can see that has a height here of 1 over pi squared. And then, if you look at that, well, the width is z minus pi. And this is valid for z, in this case, z greater than minus pi, and less than 0. Can everybody follow me on what I'm doing here? Now let me show you one other thing. Remember, when you convolve two functions, you know the total width of the convolution of two functions, both with finite width, will be just the sum of the widths of both. Do you remember this? How many do? Convolution is critical. You get this in the upper level classes all the time, at least communications. You had it in signals and systems. You're getting it here. You're going to have it in, well, it depends on the path you take, but anything that does signal process, digital signal processing, or digital image processing, radar, I can think of just about every course. Matter of fact, outside of fabrication courses, I don't know of a place you're not going to get it. And maybe you won't get it in the upper level RF design, but it appears everywhere. That's the reason I say, first exposure to convolutions, I hate it. And I hate it too, but I have to deal with it. And if I had to do this problem my own way, I'd just do Laplace transforms of both sides and multiply them, but I'm not going to go that route because this expansion is a little longer because you have a phase though. So if I look at this, and we could go also from 0 greater than z less than pi, it's going to have a 2 pi. Let me just get to this because I've really been spending a lot of time on this. When I look at my f of b here, it looks like minus pi to pi. This is a nice one. Comes here, and minus pi to pi, and the height of this right here is just 1 over pi. Now you can see, if you just take the area of this triangle, it's pi times 1 over pi is 1, right? But it would be multiplied by half, then you'd have to add that. It's exactly right. Can you all see this? That it will have a total area under there of 1. Now that's my f of b right here. Can you see it? I'm just going to do this graphically. You can do it And over here, it's gonna be a slightly different variation of this. Basically, I think it becomes pi minus c there, but you can mess with that thing and see that it's actually perfect. If you have, just flip this, make pi minus c there, and you'll graph that. Okay? Now, the original thing is I have to find the probability of b being greater than 0, less than 60 degrees, right? And it's plus or minus 60 if you want the truth, right? We can do it that way. Now take a look at that. Here's 60 degrees, and 60 degrees is what? Isn't it pi over 3? I hope so. Can you all see that? So when we talk about the probability, and they want A less than or equal to 1, which translates to B somewhere between minus pi over 3 and plus pi over 3, and minus 60 and plus 60. Can you all follow me? So it's this area here that I'm trying to highlight. Probability of B being greater than, I'll just put minus 60 degrees, less than 60 degrees is this. Now listen to the way I do it. You can write an equation for this. You can do anything you want to get that area. But the total area is 1, right? Can you all see it? So if I take 1 minus 2 times the area of that triangle right here, because that triangle and that triangle here are unaccounted for here, right? I know that the area in white plus the area shaded is equal to 1. So if I take 1 minus the area in white, I would get the shaded area. Do you see how that's a nice right triangle? And the slope of that is 1, which is nice. So it's really going to be 1 minus, can you all see that this slope is, if you look at this thing, the rise is 1 over pi, the run is pi, the slope is 1. Can you all see this, class? So if I take 1 minus, and it would be 2 times the area right here. Well, that's going to be, that has a width of 2/3 pi. And the rise on this is going to be 2/3 pi too, because the slope is 1. Or I'm sorry, over pi. So it's really going to be times 2/3 over pi. And the slope of this, if I take it in terms of the actual x and y value, this is minus 1 over pi. But if you do it this way, I want you to see the pi's will cancel. And you're going to get 1, that's how I did it anyway. And this would have a half right here, too. Then it'd be 1 minus quantity 2 over 3 squared. I'll get out of your way. 1 minus 4/9, 5/9. And I'll tell you one thing about this problem. I spent about it's over 45 minutes on this thing, just doing it. Well, maybe less than that because I was talking with you. But you see how complex this is. How many different things you have to consider for this problem, with me? And to get it right, you have to know how to do every part of it. Be aware, that's not easy unless you spend time. You have to spend time on this stuff because you can really fail in so many ways. Anyway, at the bottom line, this is 5/9 for this one. You do several problems with this level of difficulty, and you get better and better. Finally, you can do these things fairly efficiently. It's like circuits problems. The first time you see a circuit where you have to do mesh or loop analysis, and there's more than 2 or 3 loops, it looks overwhelming. But after some time, you get good at it. I think everybody knows what I'm talking about. You all went through circuits, right? How many had Irwin? Remember Irwin blasted you with homework continually? Tons of homework. That's the way you got good at it. Same way here. All right. So anyway, I think that's right. Can you just check on that one?
That's right.
Okay. That's the first part. The second part is something similar, but what is it?
It's that A is less than or equal to 1/2.
Okay. Now, it starts back. What is A equal to? Well, A in this case is what? 2 cosine of b, after all is said and done. Y'all agree with that? Remember I made that substitution of psi, or of theta minus psi over 2 is b. Y'all remember that, class? So we've got the density function for b. That's all we need. So, remember, you don't have to go back to square one and start again. We've got everything we need, we just need one other thing. If they want the probability of A less than a half, right?
Less than or equal to, yes.
So what is that? That would be 1/4 equal to cosine of B. So it's really the probability of the cosine less than 1/4. Do you all follow me? Now, I don't have my handy dandy cosine waveform, but now we just need that angle. So, I think it's wrong in the solutions. I didn't double check that. But, so what is the inverse cosine of 1/4? Give it to me in degrees.
75.5 degrees.
Anybody confirm that?
That's what I got.
Yes.
All right. Now, when you look at a cosine waveform, here's 75 degrees, or 75.5 degrees. Here's minus 75.5 degrees. With me? Less than that. What does that translate to over here? I guess I need it in terms of radians. I hate radians. So what I need to do is modify this, because I think you know what I'm talking about now. What I'm going to do, less than 75.5, can you give that to me in radians? It's some weird number. I won't even execute this whole one, but I'll tell you what it is. And you can do it. Remember, this is B here.
1.32.
Is that right? 1.32 radians? Okay, so that means over here I have minus 1.32 radians, and here I have, that's 1.32 radians. Now look, for the cosine to be less than that, right, it would be 1 minus the probability of the cosine being between it, right? Can you all see that? So I can say this. Well, maybe I just get this anyway, but you can see these two triangles here represent the angular probability, or the probability of f of b being, if I take this triangle right here, and this triangle, add them to the areas under them, I get the right thing. Now the problem with this one is, this is a little irritating. Because here, if I look at this, let's get the pi out of here. Let me try this real quick. So if I take care of the pi, I should get this. 1 minus 1 plus 1. And can you take 1.32 and divide it by pi? Anyone?
0.4202.
Okay, so here's what I'm gonna do. Since I know that slope is 1, you tell me if this is right. Jared, follow me on this. I need, this width is going to be equal to, I'm gonna take width, all right, times height. The height and width are the same because the slope is 1. So the width is gonna be 1 minus 0.426. I'm gonna square that thing, and that should be, because that times a half is this area, and there's also gonna be a subsequent take, you tell me what we get for this. 1 minus 0.426 and square it. What do you get? That should be the right answer. Anybody?
It was 0.420, not 0.426.
What's that?
0.420.
0.420. So what do you get when you take 1 minus 0.420 and square it?
0.3364.
Does he have that, Elijah? Last
It's
answer.
hard to read. He has one answer, but then he draws an arrow. to say
That's what, is this his answer?
That's there. Yes.
His answer? Okay, that's the right answer. But I'll tell you the problem. Yes.
Sorry, why did you divide 1.32 by pi though?
What?
Why did you divide 1.32 by pi?
Because I want to scale this thing right. Look, when you look at this thing, see how pi's are everywhere? If you divide out pi in the horizontal axis, you have to multiply in the vertical axis by pi. I mean, the area has to be 1. If you multiply the vertical, that becomes 1. Horizontal has a width from 1 to minus 1. It's just a trick. You do that. But these are little tricks. Back in the day, we didn't have calculators, and I hated slide rules. Anybody ever use a slide rule? You know what? How many know what they are?
I've seen one.
Well, if you're used to them, they're faster than calculators, right? A lot of things, especially logarithms. But if you're not, you better have good eyes, because the increments in those things are crazy small. You have to get a magnifying glass. Anyway, that's the way to calculate without any electronics. All right, tough problem. You gotta admit that. That's the kind of problem you don't want to see. But if you do several, it's okay, you'll get it. There's so many little things that are tricky there. All right, that's what I wanted. Next. I've used an hour. This is over 11. Oh, God. No.
No problem.
Yeah, it's a pain. I want to get right into section. I'll tell you, I want you to do the problems in section 5. Please do them in any questions you have. I'll work through them with you next time. I want to make sure you get that out of the way, and it'll drive you nuts if you don't do it now, because then it'll drive you out of your mind. So, how many of these problems I've done? Too many. Now, what we're going to do is get to section 7 in the book. And you got my book, and this is the characteristic function. We're not going to do the characteristic function. We're going to do the right function. So here's something where this is called the characteristic function. I always ask this, but is it going to rain?
I haven't seen anything for today. I'm sure.
Well, yesterday I got up. It was at most 5% chance, I think in the evening, 10% chance of rain on WeatherBug, and I think on weather.com. And then I try to go swim. 3 o'clock, it was like, these guys don't know what to do.
Looks like every day except for today this week is supposed to rain.
I just think it's too hard to predict because there's too many variabilities. But I will say one thing, if you pay money to AccuWeather, these groups work with the military and stuff, they'll get it down to a localized thing. What they do is regions of the country, and they'll give this. It may be from Birmingham down to Columbus in a swath, like with a radius of that. Well, guess what? There's a big difference between the weather in Columbus and Birmingham, but the average will have you for accurate. But if you pay money, they're very accurate. I don't pay money. State Farm pays money, I found that. Because they have to know if it's going to rain if they're inspecting hail damages. Anyway, back to the next part. This is the characteristic function. And we might put an X to that. We're not going to use this. We are going to use either Fourier or Laplace transforms. So you might say Laplace. T forms. Why? Because it makes life easy if you're doing things related to functions that you can convolve. So what is the first, let me just give you a little background so you heard it here first. What is the characteristic function? Well, don't write this down, just listen. Don't write it. Characteristic function is this. They use a symbol. Well, it doesn't matter what they use for this, but it is this. It is the expected value of a random variable, but it's not the random variable itself. It's e to the j x with a u. X is a random variable. U is something for a transform. You with me? And what they do, just so you understand what they're up to and how. So they want the expected value of something where x is a random variable and u is a transforming variable. That has an extent from minus infinity to infinity. Can you see the Fourier transform coming out of this one? Almost. So what does it actually mean? It means we have an integral from minus infinity to infinity of the density function f of x times the function e to the j u, and this is going to be x. Now it's small x, because we're going to do the integral of this thing, dx. How many see that is almost the Fourier transform definition? What do we need to do to make it a transform, a Fourier transform? Let me put down what the Fourier transform is right here so you can see. If I want the Fourier transform of a variable, I'm just going to put it as a function of omega here. That's actually equal to the integral from minus infinity to infinity of f of t times e to the minus j omega t dt. Now, y'all recognize that? That's the definition of a Fourier transform, right? You use Fourier all the time as engineers. So forget W, make it U. Remember, W is just a dummy variable too. And instead of T, make it X. And instead of a minus, make it a plus. And can you see how this is the Fourier transform in essence? Can you all see this, class? I say that because Fourier transforms have one big problem now, one irritating problem. Remember, there's a whole class of functions you can't take the Fourier transform for exactly because there is no damping. Remember, the Laplace transform, it's either j omega t plus sigma. Sigma is an actual real value, right? And that's called a damping constant, and it can make functions, you can get transforms for things that you wouldn't with a Fourier because it would blow up. It would go to infinity at the actual singularity at zero typically. Without too much more said, so how does this apply to some of the things? The real thing is this. When we have this characteristic function, we can easily get the mean and the mean squared value. And that's the reason. So let me, instead of the characteristic function, I'm going to show you the Laplace transform. So if we have something f of x, right? And we have a function. I mean, this is a density function. And we have a function. Maybe I should do this in terms of Laplace transforms and then show you how it relates directly. For Laplace transforms, you know, if you have, I'm going to call this f of, I'm going to call this f of p and f of s. And you know that f of s is equal to the integral from 0 to infinity of f of t e to the minus st dt. Now that's just the fundamental definition of a single-sided Laplace transform. Does everybody recall this? Just making you aware. You should be able to write that down without any hesitation. Sort of like Ohm's law and the basic sense V equals IR, because this is stuff that makes you different as electrical engineers from physicists in general. So I know if that relates to this, then I know if I take this and I take a derivative of f of s right here, with respect to s, I actually get an integral from 0 to infinity of minus t times f of t e to the minus st dt. Do y'all follow me? Because if you look at this, when you take a derivative with respect to s, only the minus t comes out in front, and everything else is the Laplace transform. Just hang with me. So if I look at this, and then I multiply, if I look at this by a minus sign, now I have that, right? Let me show you this. Now translate into, remember when you're doing a transform, it doesn't have to be time in s. It can be a spatial component in s. These are just properties relating abstract ideas one to another. You with me, class? So when you come here, if I say minus the Laplace transform with respect to s of this is equal to, now I'm going to do something, I'm going to take t and I'm going to make it x, and f of t here becomes f of x. So that becomes an integral of x times f of x, right? E to the minus st, or sx, pardon me, dx from 0 to infinity. Can y'all follow me? Now, watch this. If we let s go to 0, I want you to just see this. When I let s equal to 0, can you all see that's the definition of the moment? We got x times f of x integrated over range. Now there is one stipulation here. All the events, the density functions, have to be for 0 and greater than x, right? So there's modification ways. If you have an event that starts at -2 or -3, what you do is just simply create a new reference frame where you move everything down to start at 0. And at least the idea should ring true with you. There's a way to do it. Now hang on with me here. So how about an example of how to do this? First thing. And remember, don't worry about this thing, because this isn't going to buy you much. There's no tables for this. There's no familiarity. Yeah. So suppose I have a density function. This is real simple. F of x, it can be irritating, equals, and suppose you had no calculator. Let's do that. Is going to be equal to, let's see, 3 e to the minus 3x u of x. Okay. Now that should be something you're familiar with, right? That's just an exponential decay. And now I want the expected value of x. Now, normally what you do is what? Take that, multiply it by x and integrate it, right? And in this day and age in your calculators, it's pretty easy to do, right? I want to tell you some of the integrals you can come up with are not that easy. But the Laplace transform, a lot of them become easy. So if we take a look at this one, and think about this, basically here. Let me just say this. Now think of x as t. And I'm going to have f of x here. Or no. I'm going to have f of s on this side. And I'm going to have f of, actually, I don't want to do it that way. I want to do f of x just like you would do f of t. Think f of t. And over here have f of s. So if I have 3e to the minus 3x, u of x here, that translates to 3 over s plus 3. Think of it in terms of time. If you had 3e to the minus 3t, u of t, most of you should know that is a Laplace transform of that is simply what? 3 over s plus 3. How many know that? You with me? Okay, now if that's the case, now I want the mean value of that. You with me? So I have this. What did I say to get the mean value you do? You come over here, and the first thing is you take the derivative of the Laplace transform you got of that f of x with respect to s. You all with me? So when I take a derivative of this, derivative with respect to s of 3 over s plus 3, I get what? 3 over, and this is going to be s plus 3 squared, right? But since there's, isn't that a minus sign right there? Y'all with me, class? I'm going to see what I did there. If you take a derivative of 3 over s plus, the s plus 3 down here, the derivative, you could put 3 times quantity s plus 3 quantity to the minus 1. Then you take a derivative, you get a minus 1, s plus 3 to the minus 2, and it comes down to this. Now, what did I say you have to do? You have to put a minus sign in front of that. Makes that plus, right? And then you evaluated s equals 0. So what happens? That means the mean value of x is going to be equal to 3 over 3 squared, or 1/3. You can check it's right. That's easier than an integration by parts, in my opinion. Now, how do you think you get the second one based on what you see up here?
Just a double derivative.
Now you're going to take not just one derivative, now you're going to take a derivative of this, right? As a matter of fact, you can leave the minus sign in here. When you take a derivative of this with respect to s, can you all see that you're going to get a t squared out front? Y'all with me on this? How many see this? You don't? Let's try it. I want to make sure you see this. I mean, I'm putting, let's go to this one. You see if I take a derivative of this, I get t, f of t, e to the minus st dt. Do you see that? And if we let s equals 0 and evaluate this, I replaced x with t here so you can see it better, then you'll get the mean value. Now if you take another derivative of this with respect to s, you get another minus t coming out. Can you see that? Because you have e to the minus t. So now I can say, if I want the expected value of x squared, now I go ahead and simply, it's going to be minus a minus or plus, second derivative of f of s with respect to s squared, and then set s equal to 0, and evaluate it, and you'll get it. You with me? Now that would be, that's actually going to be what? That's the mean squared value. You with me, class? Because now you're going to take t squared, or like x squared times f of x. Gets a little confusing. Let me finish this thought. That was 11. 1. So if I take, to get to the point here, look over here. If I take another derivative of this, right? Matter of fact, you can put the minus sign back in front here. Another derivative of that, what happens? I get minus 3, and it's going to be over s plus 3 cubed, right? And then when I still have to take a derivative of that. You all with me? So I'm going to have minus 2 coming out in front. So that's going to be 6 over s plus 3 cubed. And then I have to let s go to 0. So I'm not bored, so when I let s equal 0 here, I get 6. Basically, this is going to be the mean squared value is going to be equal to 6 over 3 cubed. All right, so 3 times 3 is 9, times 3 is 27, so it's 6 over 27 would be the mean squared value. Can you follow me, class? How many see that? You see it in the back? Finally, last question and you're done. How do I get this? How do I get the variance? You don't need to do it.
Square the first one.
That's right. You've got the mean squared value minus the mean values. We got both. With me? I'll tell you, that's handy dandy thing to do if you don't wanna do integration by parts and a lot of things, because I'm gonna level with you. There's a lot of things where you're gonna get x squared times some f of x that'll drive you out of your mind. And I think on your calculators are pretty good at doing that. I'm pretty sure. But it's easier this way. Yeah.
So for the second derivative, is it not negative?
Well, there'll be two minuses coming out from the first, so it'll cancel. Remember, the mean, you have to take minus the derivative of f of s with respect to s, right? For the second, you get
Oh,
the,
minus, minus.
yeah, it's
Okay.
plus.
So then the third would be negative again.
Yeah,
Alright,
you don't need a,
third one would be.
if I start asking third models, then go talk to the department chair. He's bluffing with the derivatives. So. All right. I was trying my best to whip through that first problem, no matter. I thought about